Hello, in this video we are going to build a half-wave rectifier circuit and measure the harmonics and power factor of this circuit. So I am going to start from scratch. We pick up a diode from the bottom toolbar and resistance. So we are going to use a resistive load and a pure sinusoidal voltage source. We use the wire to connect all these three components in series. Now we can add some meters, current meters, DC current meter. We insert it like this, and I am going to use two AC current meters, one for measuring the true RMS and one for measuring the AC current. I am going to add a voltmeter, AC voltmeter, convert the input AC voltage. Connected in parallel with the AC voltage source, and we pick up a reference ground, 0 voltage reference ground, and two channels oscilloscope, and a current probe to display the current in the circuit. So we flip this current probe vertically and use channel A to display the input voltage waveform and channel B to display the input current waveform. I am going to zoom in to make this circuit bigger. For the resistor, I'm going to change the name from R to just R. We have only one resistor in the circuit, and I'm going to change the value to 171.4 ohm. I'm going to choose to display the name and the value of the resistor. I chose 171.4 because in lab volt equipment, with lab volt equipment, we can choose this value. We can obtain this value of 171.4 ohm, so we can repeat the experiment later on using lab volt or Festo equipment. For the current, for the DC current, I'm going to change the name to IDC and choose to display the value during simulation. And for the current AC current meter, I am going to use this meter to measure the true RMS value of the current, and for true RMS value I have to include all the components of the current, so I am going to change the cutoff frequency to 0 in order for this measurement to be true RMS measurement of the current, because by this way we can include all the components of the current, all the harmonics plus the DC component. For AC current measurement, we are not going to include the harmonics, the DC component, sorry. We are going to include all the harmonics, but we are not going to include the DC component. For this reason, we are not going to change the cutoff frequency. With cutoff frequency of 10 Hertz, the DC component will be excluded from this measurement. For the voltmeter, I'm going to change the name to VS, source voltage, and show the probe value during simulation. No need to change the cutoff frequency because this is a pure sine wave. With the pure sine wave, we have the true RMS equal to the fundamental component RMS because we have just fundamental component in this voltage source. I'm going to change the amplitude to 141.5 because if you divide 141.5 divided by root 2, you will have an RMS of 100 volt. So you can enter only the peak value. So the peak value is 141.5 to get 100 volt RMS voltage. The probe name, I'm going to change it to capital I, small s. This is the current probe, the name of the current probe. So I'm going to choose to select the name. And we need one last thing. We need a simulation control. If you go to simulate, you can choose simulation control. You can place it anywhere. And I'm going to change the total time to 0.02 seconds. That's 20 milliseconds. It's going to cover a complete cycle for 60 Hertz waveform. And on top of that, I'm going to add 1 more second to avoid the transient. So 1 more second also for the print time. So by this way, I can avoid any transient in the circuit, any transient inside any meter, or if we have a capacitor or inductor, because we want to do the steady state analysis. So we don't care about transient in this experiment. And I'm going to select free run. Close this window. Now we are ready to run this circuit. So I'm going to bring the oscilloscope window here. So if you run the simulator, you will see the voltages are coming. It's not stable. Hit on, trigger on to stabilize it. And we have two waveforms. The red one, which represents the input AC voltage source and voltage, and the second one is the input current. So we have half-wave rectified waveform for this half-wave rectifier circuit. I am going to change the orientation of this measurement. Okay, to be like this. Now, to display the harmonics and the current, we click on save. Save waveform, give it a name, choose any name. Okay, so you can choose, for example, you can choose test, for example, test 1, choose any name, save, and you will have this window. Click on channel B, or scope B is channel B. Add this variable, click on OK, and you have this current waveform. Now we can do more analysis on this waveform. using fast Fourier transform analysis, which is going to give us the harmonics content of this waveform. We can change the x-axis to display harmonics from 0, not from 10, from 0 to 1200, for example, because we don't have significant harmonics after 1000 hertz. And I'm going to change the scale to linear and deselect auto grid and put a grid spacing of 60 hertz. Okay, and you can see we have now all the harmonics, all the components of the harmonics. The 60 hertz component, the fundamental, has an amplitude of around 0.41 ampere. So this is the amplitude or the peak of the fundamental. This is the peak of the second harmonic, and this is the peak of the fourth harmonic. 240 is 4 times 60, so this is fourth harmonic, sixth harmonic. We don't have third harmonic and fifth harmonic in this waveform. So the DC is around, if you hover around the peak, you can see the measurement on the bottom left corner. So the DC around 0.261, 262. If you compare this reading with the measurement, here you can see IDC is 0.262, and this is the same value. You have it here, 0.262. The peak value of the fundamental is around 0.415, and I'm going to show you soon how to measure, how to display this value during simulation. Now, if you compare the readings of all these three currents, the RMS value and the AC value and the DC value, you can see that you can prove that I RMS square equal IDC square plus IAC square. This is equivalent to this formula, I RMS equal root of IAC square plus IDC square. IDC is the DC component of the current. IAC represents all the harmonics from first harmonic to the end. So the RMS value of all the harmonics. True RMS should include all the harmonics, all the AC harmonics plus the DC component. So if you do this on a calculator, you can prove that. You can input the square of this IDC plus the square of IAC should be equal to the square of IRMS. Now I am going to add another useful block in harmonics, the total harmonic distortion analyzer, or block THD. So the input for this block is the input current, so we want to find the total harmonic distortion of the input current, and this block generates two outputs. One output is the total harmonic distortion. If you double click to see the properties of this block or the parameters of this block and click on help, you see that the upper output is the total harmonic distortion value. The second output is the fundamental frequency, but this is a waveform. It will be an AC voltage for the fundamental. We don't need that, but we need to see the total harmonic distortions. To display this value, we need this voltmeter to display the total harmonic distortion. So I'm going to stop the simulator and run it again later. So I'm going to change the name of this voltmeter to total harmonic distortion THD, and I'm going to select show probe value during simulation. So we are going to measure the total harmonic distortion, and also we are going to use another useful block, the FFT block, fast Fourier transform block. And this block is also having one input and two outputs. So the input is the input current signal, and the output, one output is the amplitude of the fundamental, the other output is the angle of the fundamental. So to display those values, I need to pick up an instantaneous voltmeter, and I'm going to name this I1 peak. So this is the peak of the fundamental or harmonics number one, and I'm going to select to show the probe's value during simulation. I'm going to add another voltmeter to measure the angle of the harmonics. So I'm going to name this angle 1. So this is the angle of the fundamental with respect to the input voltage source. I'm going to show the value, the display the value during simulation also. So let us move this a little bit, and the other name also. Okay. Now we can run this simulator, and we have a total. Now we are measuring the total harmonic distortion, which is 0.991. This is the total harmonic distortion we have. So we have around 99% of harmonic distortion. Too big, because this waveform is not sinusoidal anymore. The peak value of the fundamental is 0.412, which is the same value. If you go to the fundamental and if you hover over the peak here, you will see on this corner the peak is 0.41, around 0.412, 0.412, 0.413. So this is the peak of the fundamental, and the angle of the fundamental is almost zero. Theoretically, it should be zero for this circuit, but it's not zero because of some rounding of errors. Now, next step, I am going to measure the power factor, the circuit. To measure the power factor, we need a power factor meter. So we have VA power factor meter. This meter, I am going to use this meter for the measurement, and I am going to insert it somewhere in here. Okay. So this meter has two inputs, and it has two terminals for the input and two terminals for the output. I'm going to remove this piece, this little piece, delete. Okay, now we can measure the power factor. Unfortunately, there is no output to measure, to display the value during simulation. So what are we going to do to display the value of the power factor? If you see, there is a variable that is flagged Okay, power factor display flag. We can display this value using the sim view, and to do that we need to unselect free run and run the simulator. Now we have this window of variables, available variables. We can select the variable name, power factor, add it, and click on OK, and we have the value of the power factor, which is fluctuating between 0.722 and 0.692. The average value, we take the average value, which is around 0.707. So the power factor in this circuit is actually 0.707, same value shown in the theoretical lecture we have taken last time. Okay, that's it for today. Hopefully I will have time to show you the same experiment on real equipment, not on a simulator. Thank you and see you next time.